This is part 3 of the video notes for Objective 9, trigonometric form of complex numbers. In the last part of the video, we looked at multiplication and division of complex numbers, either in standard form or in complex form. And in this video, we want to look at powers and roots of complex numbers, either in standard form or in complex form. So let's start by thinking of a power. We know that a complex number in trig form looks like this. And we know from the formula in the last video that multiplication of complex numbers in trig form is the product of the modulus and the sum of the arguments. And I'm going to add some extra parentheses here. So if you can imagine that an exponent is just repeated multiplication, and we needed to say do z to the squared to the second power, we would write r times r, or r squared, and then we would add theta to itself, and we would get 2 theta. Well, if we wanted z to the third power, we would multiply z times z squared, which would be r times r squared, and we would add the argument theta plus 2 theta. And this pattern goes on indefinitely, which leads us to de Moivre's theorem. So de Moivre's theorem basically says that the power of a complex number in trigonometric form is r to the nth power cosine of n theta plus I sine of n theta. And that's de Moivre's theorem. So let's give that a try. Let's say that you've been given the task of taking 2 plus the square root of 3i to the 5th power. Now, you can use binomial expansion theorems that you may have learned in another class, or you can multiply 2 plus 3i 5 times, or what we're being asked to do in Objective 9 is use the trigonometric form and de Moivre's theorem to find this power. This would be z to the 5th power. So let's go through the process of rewriting this complex number in trigonometric form so that we can find its 5th power. We start by finding r. I like to draw a picture. This is 2 comma rad 3, which would be in quadrant 1 with an x of 2 and a y of rad 3. I can find the hypotenuse either by using the formula for the modulus of a complex number or by using the Pythagorean theorem. Whatever you're most comfortable with works in this case, and we find that the hypotenuse is radical 7. So I know that r is rad 7. The next thing I need to do is find the angle. And because this is in quadrant 1, I won't need to use reference angles or rewrite it in the correct quadrant. I can simply say that theta is equal to the inverse tangent of rad 3 over 2. So let's take a look at what theta would be. For this result, we find that theta is approximately 41 degrees. Now that we know r and theta, we can go ahead and use de Moivre's theorem. Z to the 5th power is equal to rad 7 to the 5th power times cosine of 5 times 41 plus I sine of 5 times 41. We're going to simplify, and we are going to leave our answer in standard form since the question was presented in standard form. This gives me 49 rad 7 times cosine of 205 degrees plus I sine of 205 degrees. And for my last step of simplification, I need to go ahead and evaluate these numbers. And because 205 is not on my unit circle, I am going to leave my answer as a simplified decimal. So I get that z to the 5th is equal to 49 rad 7 times negative 0.906 plus, or really minus, 0.423i. Last step is to distribute 49 radical 7, and I can conclude that 2 plus rad 3i is equal to 49 rad 7 times negative 0.906, which is negative 117.5, minus 49 rad 7 times 0.423, (54.8i). And I have found the 5th power of 2 plus rad 3i. So De Moivre's theorem allows us to find the nth power of a complex number. The next thing we need to do is find the roots. De Moivre's theorem tells us the powers of a complex number, but can also be used to tell us the roots of a complex number. Be sure that you know what roots you're looking for. Are you looking for 4th roots, 5th roots, or nth roots? And then we can apply the theorem for the nth roots of a complex number. And this formula is a little bit more complicated, but it is derived from De Moivre's theorem. So we start with r to the 1 over n power. So if you remember with your rational exponent rules, the nth root of a number is the same as x to 1 over that root. And that's what we're using here. So we're keeping it as an exponent, a rational exponent, but it does really mean the nth root. And so we take the nth root of the modulus. And that's really, the factor or the length, and it's going to be common for all terms. And then to find each root, we actually need a slightly more complex formula. So we're going to say theta plus 2 pi k. We've used this notation before when solving equations, over n, plus I sine of theta plus 2 pi k. So in this example, this is similar to finding all real solutions. When you're trying to find all real roots, you're going to let k be every whole number up until 1 less than the number of roots you are looking for. So we need to use this formula, and we really need to apply it in a specific example to make sure that we understand what we're doing. I have to erase this to give myself enough room to work out the next problem, but I'll be referencing this formula as we work through it. So for example, when I said that you have to know the number of roots that you're looking for, I mean for a problem like this. Find all 4th roots of negative 8 minus 8i rad 3. So from this setup, I know that n is going to be equal to 4, and that k is going to take on the values of 0, 1, 2, and 3. And this will give me 1, 2, 3, 4 solutions for my 4th roots. From this complex number, I need to be able to find my modulus, which is your absolute value, and I need to find my angle so that I can use the formula. I'm going to go ahead and graph negative 8 comma negative 8 rad 3, which is going to be in quadrant 3, with an x of negative 8 and a y of negative 8 rad 3. With this setup, I know that the hypotenuse is 16, but you should take a minute and use the Pythagorean theorem or any strategy you prefer to find the missing side. For example, maybe you'd rather use the formula provided in video 1. That's going to be entirely up to you. Once you've determined that the hypotenuse is 16, you need to find the angle, and we're going to be saying that alpha is equal to the inverse tangent of negative 8 rad 3 over negative 8. This is a unit circle value, so negative rad 3 is on our unit circle, but we've been working in degrees for these last few examples, so feel free to evaluate this from your calculator to get your solution. And we find that alpha is 60 degrees. Notice I used alpha, and that's because my calculator for inverse tangent is always going to output an answer here in the first quadrant or here in the fourth quadrant. And for the theta, I need an answer that's in quadrant 3. So I know I can take my alpha equals 60 degrees and simply add 180. Theta is equal to 60 plus 180, or theta is equal to 240 degrees. I now know all the information that I need. R equals 16, N equals 4, and K will be each of these values separately to apply de Moivre's theorem and the theorem for the nth roots of a complex number. So let's start with the formula. R to the 1 over N cosine of theta plus 2 pi k over N plus I sine of theta plus 2 pi k over N. As I plug in my values, I'm going to adjust my formula slightly to be in degrees because right now I know that 2 pi k is 1 rotation in radians. So I'm going to start with R. R is 16, N is 4. Cosine of theta plus, switch 2 pi to degrees. Oh, and we can go ahead and substitute what we know theta to be, which is 240. And then do the same thing for sine. And then I am going to find each of my 4 answers by substituting k equals 0, k equals 1, k equals 2, and k equals 3. And so here to the side, k equals 0, k equals 1, k equals 2, and k equals 3. Let's start with 16 to the 1/4 power. 16 to the 1/4 power is 2. If you plug in 0, you get 240 plus 0 divided by 4, which gives me cosine of 60 and sine of 60. If I plug in k equals 1, I get the cosine of 240 plus 360 divided by 4. Which is 150. And when I plug in 2, I'm going to be doing 240 plus 720 divided by 4, which gives me 240. And when I plug in 3, I'm going to get cosine of 330, sine of 330. Again, when the problem is given to you in standard form, your answers should be in standard form. So these are the trig forms of the complex answers, but I'd like to find the standard form of each of the complex answers. So I'm going to figure out what cosine 60, sine 60, cosine 150, sine 150, cosine 240, sine 240, and cosine 330, sine 330 are all from my unit circle. I'm going to leave the 2 out in front, so I'm showing each step, but I will just be taking my answers and multiplying them by 2. Cosine of 60 degrees is 1/2. Sine of 60 degrees is rad 3 over 2. Distribute the 2 and you get 1 plus rad 3i. Cosine of 150 degrees is negative rad 3 over 2. Sine is positive 1/2. Distribute the 2 and you get negative rad 3 plus I. Cosine of 240 degrees is negative 1/2 and sine is negative rad 3 over 2. Distribute the 2 and you get negative 1 minus rad 3i. And the last one is 330 degrees where cosine is positive rad 3 over 2 and sine is negative 1/2. Last time to distribute the 2, and these are the 4th roots of the complex number negative 8 minus 8I rad 3. The last thing we want to do is the application of finding the nth roots. So why would you need the nth roots? Basically, we need to find roots when we're faced with an equation that has an exponent. So the example that I would like to use is x to the 7th minus 64x equals 0. I'm going to use my nth roots of a complex number to solve this problem. The first thing I want to do is go ahead and factor out an x. This gives me my first solution of x equals 0. For this problem, I'm trying to find the 6th roots of 64. So 64 is the complex number. Basically, I'm saying x to the 6 equals 64. So what are the 6 roots of 64? That's what I'm trying to find. Well, if 64 were a complex number, its trigonometric form would be 64 cosine 0 plus I sine 0. Because if you graph, or if you think of 64 as a complex number, it would be 64 plus 0i, and we would graph it on the positive x-axis. Its modulus would be 64, and its degree would be 0. These are supposed to say 0, not theta. Okay, well, if that is the case, then I can say that r is 64, theta is 0, and n is 6. And I can use the nth root of a complex number to solve. So the nth root of a complex number is r to the 1 over n times cosine of theta plus 1 rotation k over n plus I sine of theta plus 1 rotation k over n. Substituting the values from my problem, I get 64 to the 1/6 power cosine of 360k divided by 6 plus I sine of 360k divided by 6. And I can actually simplify this further, so I'm going to. And I'm going to say that this is 60k and that this is 60k. So my answers are all going to be in the form of 2 times cosine of this. For k is 0, k is 1, k is 2, k is 3, k is 4, and k is 5. Remember, I'm looking for 6 solutions when I'm trying to find the 6th root. So I'm going to say 2 times cosine of 0 plus I sine of 0 for when k is 0. Then I'm going to say 2 cosine of 60 plus I sine of 60 for when k is 1. 2 cosine of 120 plus I sine of 120 for when k is 2. Leave a space for my answers. And then I'm going to repeat the process for my next 3. 2 cosine of 180 plus I sine of 180. 2 cosine of 240 plus I sine of 240, and 2 cosine of 300 plus I sine of 300. Now for this example, because all of these are in the unit circle and I'm distributing a 2, I'm going to go ahead and not show my inner step. I'm just going to eliminate the denominator of 2 since it will be eliminated by multiplying by 2. Cosine of 0 is 1 times 2 is 2. Sine of 0 is 0, and the imaginary term eliminates. So one of my solutions is 2. Cosine of 60 is 1/2 times 2 is 1 plus sine of 60 is rad 3 over 2 times 2 is just rad 3. There's my first imaginary solution, or complex solution. Cosine of 120 is negative 1/2 times 2. Sine of 120 is rad 3 over 2 times 2 is rad 3. There are my first 3 solutions. Only 3 more to go. In the next step, cosine of 180 is negative 1 times 2 is negative 2. Sine of 180 is 0, so my next solution is a real solution, negative 2. Cosine of 240 is negative 1/2 times 2 is negative 1 minus sine of 240, which is going to give me rad 3i. And I'm just squeezing in the I just barely because I'm out of room on my board. Last but not least, cosine of 300 degrees is positive 1/2 times 2. Sine of 300 degrees is negative rad 3 over 2 times 2. Let's add them all up. When I first began the problem, it was x to the 7th power, which meant I had 7 solutions. I found the first by factoring out an x, and then I found the remaining 6 by finding the 6 roots of 64. Notice 4 of the solutions are imaginary and 3 of the solutions are real. This concludes the video notes for Objective 9, Trigonometric Form of Complex Numbers. Be sure to try the practice problems in your textbook located in sections 6.2 and 6.3.